Okay, we continue our discussion the derivation of the conservation laws. Before we draw that one is we call this material derivative. In here, that one represent any intensive property of your system, like a raw density. It doesn't depend on the system size, so on. Then later on, we draw Reynolds transport theorem. Any extensive property like a mass, total mass on your system change respect to time, material derivative is equal to that one. Again the intensive property. So we apply that one is the conservation of the mass in here. So we obtain that one continuity equation, and this is the first form, and second form we can represent like this. Now we are in here. Let's say again we are in continuum material. The definition of the continuum was like you have some property of your system. Let's say m, the total m in your system. This we can call this function. Is the function of the x and the t. So you have some system. The system is collection of very small differential volumes or differential m. This gives the summation dm's, the collections. Then the definition of the continuity is you can express any extensive property like m by some function. If this function have the derivative in each point, this means it's continuous. There is no any discontinuity. Then you can call this continuum region, continuum region. So we call this micro, or we can move macro size. So okay, let's consider any body like this, control volume, control system. There are two type of forces can act this body like the first one is the external body forces, call this gravity, and the magnetic or electrostatic field acting through the control volume like this or this. Second type of the force acting the friction and the pressure act on the surface. Let's say you have some control surface inside of your control volume. We call this control surface. So you have some normal vector like this, and you have some vector t acting on your contour surface because of the friction and the pressure. Okay, define the F arrow is the body forces per mass like here, and Tn is function of the x position vector and the t is contact force per area acting on ds like here. In here the n we know from before as the unit normal vector is perpendicular the surface area is in here. If you go the other slides again, okay, you have your body control volume here and your unit vector, your the acting what was I forgot contact forces like friction pressures, and we can call this vector acting on the contour surface traction of stress vector. This is the force per area that acts on the surface ds, and this is also a function of the position and time and the surface orientation also at the end. So finally, for a specific control volume control system is changes respect to time and position. The contact force acting on the contour surface like S, we can write double integral of the vector of ds, but at the same time we can write the total body force acting on the volume V. We can write like this. These two things we define. and we can find them, we can calculate them by this formula. Going in the next step, then what was our uh, sorry, if we go back, so our Reynolds transport theorem say accumulation of the function at the left side in here, the accumulation of the momentum of the system respect to time, material derivative coming from that one Reynolds transport theorem, and at the right side total forces acting on the system moving with the material volume, no input or output of mass, it's just accumulation. Then we can write here the momentum of the system rho multiplied by v. Rho is the density and v is the velocity of the your fluid. Let's say you have some fluid is moving like this, has some velocity like say some rho. Rho is like say kilogram meter cube, and this is the then we obtain here kilogram. This is the respective time here. Then we obtain square. Then okay, this that one here, this term represents the total momentum change on your system. At the right side, we can write the force acting on your system. The first term is coming from contact forces because of this traction, and second one is as I showed before, it's coming from the body forces because of gravity and so on. Then I can write this left side by this form, just rho RTT coming from RTT, dv over dt, and right side we keep the same. So okay, when we continue to get the physical meaning of the each term, we go in the next slides. Okay, when we continue our discussion now here, we have this term here, and in here actually we can write this term, this vector acting on the contact vector, and this we said before, this is function of the x position vector, and the time also the function of the orientation of the. And we can write this equal that one in here. N is the arrow is the unit vector, dot product between t arrow is defined as a stress tensor. It represents the state of the stress. Actually, it's give the state of your straits on your system. The t is the stress tensor, is the dependent on your x and the t, but independent of n this time. Okay, but this depends also the n, but that one is independent of n. So we can get this, and we had before that one. Now we have that one. Instead of that one, that vector, we can write this one. So from here, from the divergence theorem, if you remember before, what was divergence theorem was saying, according to divergence theorem, this divergence of the t dv is equal to double integral on the surface and vector t ds. These are two equals because of the divergence theorem. So instead of that one, we can write that one to here. That is the divergence of t, divergence of tensor, stress tensor. Okay, we continue. Then if we take all the things in the left side, then we get the common parenthesis of dv. We obtain that one here. So this should be equal to 0. How I'm gonna get this equal to 0? Either this should be 0, this cannot be 0 because this control volume cannot be 0. This term then is gonna be 0, like in the mass, similar to mass conservation. So going to next part, then we obtain actually this equation of the motion here, the conservation of the linear momentum for continuum. Call this equation of motion conservation of the linear momentum for continuum. The left side we obtain that one. In the first term here, the external forces due to this contact force vector, this tensor, stress tensor here, and we have body forces rho and F coming. T is total stress tensor, include pressure, shear stress, and normal stresses beside the pressure. And we can write T as a S minus Pi. So this is the pressure, this is the scalar, and this is the extra stress. Then I can convert this term, that term here, so I can write here in this form instead of that stress form. This is the grad P, and this is the divergence of that term. I can write as we can write that one as in this form actually. So S or that one is a function of the deformation and or deformation rate, shear rate. What's okay? So we obtain finally that form. Then similarly, we call this the conservation of the linear momentum, conservation of the motion. The left side, accumulation of the total momentum, and this comes this stress tensor, and we can write this in this form, and this is body forces. Actually, another momentum conservation is conservation of the angular momentum. We can write the angular momentum left side in here. In the first term is this vector cross product by x position vector. To obtain the angular momentum, we just get the cross product each term by x position vector. Then we can write by this form, and we can obtain that one again right here. After that, I can write just chain rule for this form. Basically, this is going to give the 0 because why this from here to give the velocity term, the cross product between the cross product velocity itself is gonna give 0, then just obtain that one. That's 0. In here, we get this form. When we go the next step, we obtain that form here. Okay, just continue the other steps. Now it can be shown that the divergence of the cross product between the tensor, stress tensor, and a position vector is equal to a divergence of the tensor vector cross product x minus tx. So where tx is a vector defined by the tx by this form, then if we insert the equation, finally we obtain that form, is then this is gonna be equal to that one. But result of the conservation of the angular momentum, this is the 0. Then if this is a vector, clearly it is 0, then dot product between that one and the vector a is gonna give 0. A is any vector, then let's say that one, then can write the tau 1 here, and we can show this is give the result of 0. Now, the conservation of the angular momentum, the stress tensor is the symmetric. Then we obtain tau 1. This is our angular momentum derivation, because the right side is 0. Because this cannot be 0, this has to be 0. Then we can write the angular momentum, otherwise moment of the momentum, by this form. So when we continue, okay, now we are in here, mechanical energy balance. If you multiply the equation of the motion by V, in here, what was the equation of the motion? Here, equation of the motion, that one. If we get the dot product equation of the motion by V, what was our equation of motion? Actually, we can write our equation of motion by this form. We can carry this in here. Okay, what was our equation of motion again? In here, our equation of motion, rho gradient tensor, stress tensor, and rho body forces. So if we get dot product for each part, let's say we dot product by V, dot product in here by V, dot product by V, like here, then what is this term here? We can write this term by this form. This is a trace of that one. Then we obtain that one. Then we can write that is equal to d over dt. 1 over 2 is v square. From here, we can write like this. Then we can obtain from density d over dt, that one in here. We can write that term and that term. We call this form is the mechanical energy balance. In here, the left side is to give the accumulation of rate of the mechanical energy. And the first term here, dot product between stress tensor on the velocity and the dot product also by that operator, rate of the work done by this contact forces on the body, and this is the rate of the conversion of the mechanical to thermal energy here, this term, and this is the rate of the work done by the body forces, these three terms. The first one is the rate of work done by the contact forces. The second one, the rate of the conversion of the mechanical energy to thermal energy. This term is give rate of work done by the body forces, all per unit volume here. It's also per unit volume actually. Okay, this is our mechanical energy derivation continuum. So the final step to obtain the conservation of the total energy. Some statements about the conservation of energy. A body mass process energy as an internal energy, U per mass, and kinetic energy, Dou1 per mass. And energy transfer as a heat by conduction is given by Dou1 heat flux, and radiation Dou1 heat transfer due to the temperature difference. And so energy transfer by work due to external force acting over a distance, work rate given by Dou1. So total energy is conserved, no generation or no consumption as a mass. So conservation of the total energy for a material volumes can be written by this form. This time we write rho internal energy plus in here kinetic energy and so on. at the right side, we just write energy transfer from the surface. Let's say you have your control volume. You have some ds here, contour surface. So this represent you have some unit normal vector, and you have some and vector acting here. This term, this actually this g, give the uh, uh, heat transfer from the surface due, uh, due to the conduction per area is given by this term. This term is the give the radiation term, heat transfer due to temperature difference, that one on your total volume. And this term we know from that one, energy transfer by work due to external forces acting over the distance, that one. And total, then this is, yeah, this is the external forces mean contact force and body forces, two term. Actually we can write this in this form we showed before. So this is going to be this. Why this minus here? Because it's coming from the sine rule. Now we can write that one by this form because of divergence theorem. Plus this term is keep same. We can write that one in this form, and we keep that one same. Then we go into the next slides. Then we have raw internal energy, kinetic energy, is equal to that one. This is the result of in a practical way. If I take everything here and put the left side and take the common parenthesis of the dv, like others, let's say, right? If I take everything here, from here I have 1, 2, 3, 4 term at right side. Then d over dt we just put here. I just obtain 1 over 2v square minus, this actually is going to be plus 1 minus 2 minus 3 minus 4. I can get this common parenthesis of dv is going to be equal to 0 at the right side. This cannot be 0, then this should be 0. Then in the next step, as a similar to mass conservation or the momentum conservation, I obtain this form. So we call this the total energy conservations here. And from the total energy conservation, if we subtract the mechanical energy conservation term here and take this term, bring here, and this term total minus the mechanical energy, then it's gonna give the thermal energy conservation of energy balance. Then we obtain that one. This input rate of the G was the heat transfer because of the conduction, input rate of because of the temperature difference radiation, and irreversible conversion rate of the mechanical energy to the thermal energy due to the friction, that one, and reversible conversion between the mechanical energy and thermal energy due to the expansion or the compression of the fluid from coming. So far, and finally we obtain all the conservation equations here. So if you go remember, this is our conservation continuity equation, conservation of mass, that one, and these are the different forms what they are saying. Finally, then this is our next slide. We go, sorry, this is our equation of the motion, conservation of the linear momentum, and we can write also in this by this form. We can open this stress tensor, that one. We can write angular momentum by this form here. This is our these are when we multiply equation of the motion, linear equation of motion, get dot product between V, we can obtain mechanical energy balance like this. Then we can write our total conservation of energy by this formula. Then as a final step, total energy conservation equation minus mechanical energy conservation is going to give the thermal energy conservation like here. Then we obtain that one. This is thermal energy conservation. You can write in all the physical meaning, all the terms here. So finally, what we did, we get some, okay, some here vector tensor x position vector at the time is equal to t, the reference coordinates here. Then we obtain velocity term. Velocity term is given by the material derivative of the x respect t is given that one actually. Then we define Jacobian. Then we define Reynolds transport theorem and material derivative. When we took all this thing, then we first derive mass conservation, then linear momentum conservation, then angular momentum conservation. Now then mechanical energy conservation is basically dot product between linear momentum and the V. Then total energy conservation, then thermal energy conservation is total minus mechanical energies give that result. Okay, now I just finish the derivation of the conservation laws. In the next video we are gonna go to PSL and start checking the important points in each chapter and go chapter by chapter. So see you in the next video.